In this video, we're starting section 5.3 on logarithmic functions. Our goals are going to be to define and evaluate logarithms, graph logarithmic functions, and then finally we'll talk about how we can find the domain of log functions. Okay, so in this video specifically, we will focus on what logs are and how we evaluate them. Okay, so first, I want to recall that when we have an exponential function, something that looks like y equals a to the x, where that base, the a, is some number that's bigger than 1, well, the graph of an exponential function, it looks something like this. So on one side of the y-axis, it grows really, really quickly. On the other side of the y-axis, it kind of snuggles up next to the x-axis. I have a horizontal asymptote there. And remember that when x is 0, if I plug that in, the y value is 1. And that's the balance point on our exponential function graph. And if my base is something between 0 and 1, like if it was a fraction like 1/2 or something, then I have an exponential decay graph where it is kind of flipped, and on this side it is getting close to the x-axis. Okay, and the balance point still, when I plug in 0 for x, the y value is still 1. Okay, so our exponential function graphs, they look like this. Okay, so what I want to observe now about these graphs is that they both pass the horizontal line test, right? Because any horizontal line that I draw will never cross the graph more than one time. So it'll pass the horizontal line test. And because of that, these graphs have an inverse. And the inverse of an exponential function is called a log function. So I write it as log base a of x. Okay, so in words, we say this is log base a, so that subscript, I call it the base, log base a of x. Okay, so let's define this a little bit more formally. So if the base that I'm working with is positive, and as long as it's not equal to 1, then we are going to define a log function. So we're going to define log base a. When I say log base a of b equals c, well, what does that mean? So this double-sided arrow means equivalent. So we're about to write a statement that is equivalent to what this is saying. So a log is an inverse of an exponential function. So when I have log base a, I can rewrite that as an exponential statement as a to some power equals something. And I want to think about what that power is and what this number over here is. So because they're inverses, they should switch the role of the input and the output. So currently, b is the input of the log function, and c is the output of the log function. So they're going to switch spots. C is going to be the input of the exponential. It's going to be the input of the exponential. And then b is going to be the output of the exponential. So notice how they switch spots. Okay, so I want to do some examples where we get a feel for, what a log is and how do we work out what log expressions equal. Okay, so in part A, I want to compute log base 5 of 125. Okay, so let's say I didn't know what this is. What I can do is I can say, okay, let's let log base 5 of 125, let's call this thing x. Okay, so currently this equation is in log form. Okay, but I feel a whole lot more comfortable working with things in exponential form. Okay, so I'm going to rewrite this. I'm going to transform it to exponential form. And in exponential form, the base of the log becomes the base of the exponent. So I'll get 5 as the base of the exponent, and I'll get 5 to some power equals something. So the input and the output should switch spots. So 125 is the input of the log. So now that's going to be the output of the exponential. And the output of the log will be the input of the exponential. So x is going to be the input of the exponential, and then 125 is going to be the output. So notice how that 125 and the x, they switch spots, and then I switch to exponential form. Okay, so well, what's x? 5 to what power equals 125? Well, x is just 3. X is just 3. Let me also just mention that we have switched from log form to exponential form. Okay, so we started off by saying, okay, let's let this log be x, and now we've worked out what x is. So that means log base 5 of 125, well, it's just 3. Okay, so when we work out what log expressions equal, what we're really going to get is, well, what's the exponent? What's the exponent that makes it work? Okay, let's do another example. So in part B, I have log base 5 of negative 125. So again, I'll start it off in the same way. Let's let log base 5 of negative 125. Let's let this be x. And now I'm going to convert this. Let's convert this. Let's transform this to exponential form. So the base of my log becomes the base of the power. And then I switch the role of the input and the output. Okay, so that'll give me 5 to the x power equals negative 125. Okay, so 5 to what power equals negative 125? So this feels a little bit weird. That's good, because this equation has no solution. It has no solution since if I do 5 to any power, 5 to any power is always going to be positive. It's always going to be greater than 0. So there's no way it could be equal to a negative number. Okay, so we tried to figure out what exponent works to make 5 to that power be equal to negative 125, but we're not able to find a solution there. So what that means then is, well, this original problem was an expression. I was just trying to simplify it, and there's no value for it. So we say that log base 5 of negative 125, well, it is undefined. We tried to find a value, but we couldn't, because we ended up with an equation that had no solution. Okay, all right. So there are a couple of really common log bases. So sometimes you'll see a log written like this, like log of x, and there's no number written in the base. So what that means is log base 10. Log base 10 of x. It's such a commonly used base that we want to have a shorthand way to notate it. And the way we do that is we just don't write any number in the base. And that just means log base 10. The other really common form that you'll see is this thing, ln of x. So this is something called the natural log. The natural log. And the natural log means log base e of x. Okay, so we will really commonly be using ln of x as a log to work with, especially when we solve equations a bit later. Okay, so all right, let's do a practice problem involving one of these. Part C, let's say I have ln of the 6th root of e. Okay, so I'll start it off in the same way I did the previous ones. Let's let ln of the 6th root of e be equal to x. I don't know what it is, let's call it x. And now let's transform it to exponential form. So, well, the base of this log is technically an e. So I'll get e to the, and then I switch the input and the output. So e to the x equals the 6th root of e. Okay, and well, I could rewrite the 6th root of e as a power, right? Because a 6th root is a fractional power. It's e to the 1 over 6. Okay, so I got e to the x equals e to the 1 over 6. Well, so those exponents got to be the same. This exponent has to match this exponent. So my x equals 1 over 6. Okay, so that's what ln of the 6th root of e is. It is just 1 over 6, and we got the value. Okay, all right, let's end this video by doing one more example, but this time let's up the difficulty a little bit. Okay, part D, what if I have log base 1 over 4 of the cube root of 32? Okay, so I'm going to start it off in the same way. Let's let log base 1 over 4 of the cube root of 32 be equal to x. I don't know what it is. Let's let it be equal to x. And I'm going to transform it and put it in exponential form. Okay, so when I do that, the base of the log is 1 over 4. And that'll be the base of the power. And then I switch the role of the input and the output. So I'll get 1 over 4, that whole thing, to the x power equals cube root of 32. So 1 over 4 to the x power equals cube root of 32. So at this point, I actually want to give you an opportunity to try to solve this. I got an exponential equation. We've seen stuff like this before. So give yourself 3 minutes to try this on your own. and see if you're able to solve it. Pause it in 4, 3, 2, 1. Pause it and try this for about 3 minutes. All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it together. So, okay, I think it's going to be helpful to rewrite this cube root as a power. But also more generally, one of the things that I want to notice is that I want to try to get a common base here. I want to try to get a common base. So like if I look at numbers like 4 and 32, well, they're both powers of 2. Like 1 over 4 is 2 to the negative 2 power. So that whole thing is to the x. And then 32 is 2 to the 5th power. And then if that whole thing is being cube rooted, well, a cube root means I have a 1 over 3 power. Okay. And now, well, if I have a power and then that whole thing is to another power, I get to multiply the powers. So I get 2 to the negative 2x. Same thing here with these powers. If I multiply those, I get 2 to the 5 over 3. Okay, now because I got 2 to a power equals 2 to a power, the power's got to be equal. So that means negative 2x should be equal to 5 over 3. And then if I divide by negative 2, I'll get x equals, well, dividing by negative 2 is the same thing as multiplying by negative 1/2. And if I do that, I get negative 5 over 6. So I wanted to know what this log is, and I called it x. Now I know what x is. It's negative 5 over 6. And that's my answer.